Hello, my name is John Ray Rao, and I'm going to present my final project, which I did a 3-bit flash analog to digital converter. So in terms of what I'll go over, the first part, I'll go over what analog and digital signals are, and what you would expect for in terms of inputs and outputs of an analog to digital converter. In the second part, I will talk about how I implemented, or what implementation I chose for the analog to digital converter, and what modules that implementation would require. For the third part, I will explain more in detail the theory of each component in the modules, so that I can explain how my simulation, my schematic works. And in the fourth part, I will actually show my schematic working, including expected outputs from given inputs. The fifth part, I will go over problems I had in this project and what I did to solve them. And then the sixth part is just the conclusion. So first, what is an analog to digital converter, and what should it do? So it's important to understand the difference between analog and digital signals. So if you see here in this wave, it's continuous, so it can take on any range of values, infinite amount of values. But if you compare it to this digital signal, it's quantized, so it's discrete. It can only have this value or this value or this value, so it looks like a staircase. And so I made a little graph here to explain what an analog digital converter should do. Is it should take this analog, for example, this line, which is continuous in an analog. It should take it and it should output a discrete value. So for example, if it's between 0 and 1, it should produce 0 in binary. If it was between 1 and 2, it should produce 1 in binary. Again, it's discrete, so it has to be in binary. If it's between 2 and 3, it'll produce 2, which is 0, 1, 0 in binary. And so it goes on like this. And of course, these values here, I made it simple in my implementation such that the cutoff values, or in my implementation, what will determine the values here, it's going to be integers, because it's easier to just understand. So I changed the specific reference voltage to make it nice and even like this. And so again, I'm assuming in this graph that this ADC has ideal comparators and combinational logic, and such that the reference voltage, which I'll talk about later, is configured such that the cutoff values are integers. Because it's not always going to be integers. It depends on your reference voltage. So the inputs, like I said, are analog, and the outputs are supposed to be digital, continuous to discrete. And of course, it's a 3-bit, so it should output in 3-bit binary. And so there are multiple ways to implement the analog to digital converter, like the dual slope, successive approximation, sigma delta, and flash. And in researching all these methods, I chose to implement a flash ADC, analog to digital converter, because it's the easiest for me to understand, explain, and implement. And so in terms of what a flash ADC will require, it will require 3 modules. The first is the voltage divider network. The second is a network of comparators, and these output to a 8 to 3 priority encoder, which will output a binary output. And so in general, n-bit flash ADC will require 2 to the n resistors and 2 to the n minus 1 comparators. So 2 to the third is 8, 2 to the third minus 1 is 7. And this voltage dividers produce a reference voltage to compare with the comparator, and the comparator will output a digital value of 0 or 1, and this will feed into the priority encoder to produce a binary output. So basically those are the functions of each module. And to go into more theory, the voltage divider network, it has a relationship such that the voltage drop across n resistor, n starting here, 1, 2, 3, 4, 5, 6, 7, 8, counting down, the voltage drop is going to be Vref times n over 8. So For example, if Vref was 8, then this would be a voltage drop of 1, this would be a voltage drop of 2, voltage drop of 3, and so if it's going to be a voltage drop, it's going to go from 8 to 7, 8 to 6, 8 to 5, etc. And then in terms of the amplifier, in terms of theory, the ideal amplifier will have, so an amplifier in general has these positive and negative terminals, and given these terminals, given their relationship, so if V plus is greater than or equal to V minus, they'll produce VCC, which for the comparator is going to be defined to be 1 to produce the digital values. And if it's this positive value is less than V minus, then it'll be 0. So the last part, the last module, is the 8 to 3-bit priority encoder. And the way this works is it's going to take the resulting output from the comparators. So it's basically taking the input and comparing to the reference voltages here. It will output 1 if the input right here is greater than this voltage reference. So if it's, for example, here it's 7, if it's greater than or equal to 7, I'll put 1 here. If it's greater than or equal to 6, I'll put 1 here, etc., etc. And so we'll use this output from the comparators to produce a 3-bit binary output. And so the way this works is basically the top comparator has the highest priority, the lowest comparator has the lowest priority, and it'll produce a 3-bit binary based on the largest priority bit. So for example, if there was a 1 here, then it should produce 7, because that's the 7th comparator. So 7 is 111 in binary. So in summary, the voltage divider network produces reference voltages that are basically compared to the analog input signal. And then the comparators are used, and they produce a 0 or 1, a 1 if the input is greater than the cutoff value, a 0 if it's less than. And the priority encoder uses the 8-bit values from the comparators to produce a 3-bit value, such that it equals the largest priority bit. So this is how I implemented it in my schematic. As you can see, there are 8 resistors here of the same value. They're all R. And here are 7 comparators. So important things to note here is that I use voltmeters just to confirm that these voltages are what I expect them to be. So this is 7, this is 6, this is 5, this is 4, this is 3, this is 2, this is 1. Like I said, that's how the voltage divider network is supposed to work. And the other thing is, for the priority encoder, I did not manually put logic gates. I just use a 74F1489N device, which is basically already a component available in Model Sim that acts as an 8 to 3-bit priority encoder. And the important relevant thing to note is that the inputs and outputs are active low. So I had to put NOT gates here to make sure that the circuit worked. So I will show in the next slide, so given an input, what the expected output should be. So in my circuit, I put 1.0 volts, which is the analog signal, and I would expect a digital signal of 001. So you can see here in the output LEDs, a blue is a 1 and a white is 0, so it's 001. If I put a 2.5 volts, I would expect a 2 volts or 010. So this should be the only one on. I put 3.9 volts, I should expect 3 volts, which is 011. So these are the only 2 that should be on, which is true. And then finally, the 7.9 volts, I would expect 7, which would be 111. And again, it's comparing this input to each comparator to produce a value, which will then output to the encoder and then produce a 3-bit binary output. So I actually made this, but there were a couple problems that I had to figure out how to solve. The first was just understanding what analog and digital signals were and how I should implement them, because it was confusing to me when I was reading the different implementations how you were supposed to actually, how each part worked together. And so I chose the flash ADC because it made the most sense to me how each part worked. So it would be the easiest to implement, the easiest to explain, and so that's why I chose it. And I figured out how to, you know, how to make an analog to digital converter by choosing something simple. The second problem I had was these comparators. If you notice, they're ideal comparators. But before I chose a practical op amp, and that was causing problems to the reference voltage. It wasn't what I was expecting it to be. So what I did is I just used the ideal comparator, so there was no parasitic resistances or anything like that. So if it was ideal, I got exactly what I expected. And the third problem was figuring out how to implement the 8-to-3 encoder, which I solved because I figured out that Multisim already has one. It's a 74F1 for 8N. But I also had to read the data sheet to understand how to use it. So, in conclusion, I think I learned a lot. I learned what analog and digital signals are. So analog signals are like sine waves and digital signals are like pulse waves. I learned the different implementations and their respective drawbacks in choosing which one I wanted to implement. For sure, the flash ADC was the simplest, but it was also the most expensive in terms of hardware. But it's also the fastest and good when the input is sampled many times in a short period of time. And also I just learned different aspects of the ADC because what I showed here was an ideal one. So this graph might be skewed. It's not. This is assuming ideal circumstances. So I learned like what things can skew an ADC and what can go wrong. And I just want to acknowledge that I really like this project because I just wanted to understand how a computer uses digital values to actually interact with the real world. And I thought it was really cool. It gave me a greater appreciation of just how all the different circuit elements can work together to produce something actually practical and real. And I just appreciate it, learning and applying all my knowledge in circuits, giving this opportunity to make something. And these are my references. And that's it.